Hi everyone, this lesson is about the topic solids of revolution. So you can see I have a couple of diagrams drawn here. These were from GeoGebra on the online resources, which are free for everybody to take a look at, so I encourage you to do so. So the setup here is, if we look first at the left hand side, we have our normal XY Cartesian axis. We have a function here, which could be any function at all, f of x. That could be part of a periodic function, who knows. And at some point, what we want to do is we want to imagine that that curved line rotates around the x-axis. And as it rotates, it sweeps out a surface that would create, let's see, if we had a circle here and we had a circle here, and then this curve would sort of follow along like this, and we'd end up with, you know, there's the sort of the back, the base there, it'd end up like a vase. So what would be the volume of that solid that's formed by rotating a function full 360 degrees around the x-axis? And we approach this question by considering a little thin slice of this solid. So that the width of that would be delta x, a little change in the x value. You can see in the 3D view over here, I would have a radial distance across there. That's not a very good colour, is it? Let's highlight. No, that didn't work. The dark green's not helping me there. Let's try red. That's better. So I would have a radius running from there out the radius of the disk. Now, what would that radius look like over here? Well, that radius, that would be the value of the function, the y coordinate. That would be the value f of x. So let's think for a moment about what the volume of just this little slice would be. Well, it would be the area of the base. The area of the base is a circle, so that would be pi. Oh, come on, GeoGebra, don't do that to me. By the radius squared by the height of the cylinder. Now, that's a formula from middle school, really. But let's just put in here, what's our radius? We just decided that the radius of this was the function itself, f of x, which would need to be squared. And the height of the cylinder, that would be the height of the cylinder there, which we decided was delta x. Now that would just be the volume of that one slice. How would I find the volume of the entire solid? Well, let me jump over to this view for a moment. Now, this is where I generated this from. Let's just take those away. That's the view we had. My cylinder was probably a little bit thinner than the one there, and that's the sort of view we were looking at to start with, and that's the second view we were looking at. Now, if I was to make a whole bunch of these cylinders all the way along, you can start to see the three-dimensional nature of this shape filling up. And I would need to calculate the volume of each cylinder and then add all of those together. If I make the cylinders, in other words, the delta x value smaller, then there's going to be more of these things to add, but they're going to do a much better job at following along the edge of the curve. They won't be quite so chunky as my previous diagram. And you can start to see, if I make the differences, the delta x's, in fact on this screen it's shown as a dx, I think you can see where we're going to go with this. If we start to make them exceedingly small, then the shape follows exactly the function. My cylinder has become just a tiny thin little slice, and I would be adding an infinite number of these little slices together as delta x approached 0, as it became infinitesimally small. So that sounds exactly like calculus to me. Now let's go back to where we can write a few notes about this stuff, and let's write that down. We would say that the volume of the cylinder would be the sum from I equals 1 to n, however many there are, of our formula that we had developed, pi by, now I might just put y squared instead of f of x squared, because the notation we would often use, of course, for a function like this, we would say that y equals a function of x. So it's a little bit more compact to write y squared by, now that would be yi, the ith value as we moved across, by delta x, and delta x would be the same in all of these cases. Now, in the limit, as delta x approached 0, we would have an integral. And the integral would have a lower bound and an upper bound. The lower and the upper bound, well, this would be point A and this would be point B. The limits of integration would literally define the beginning and the end of my curve, and that's the bottom and the top of my shape. The pi is a constant, so we'll normally write that at the front, and then it becomes y squared dx. That's the formula for a volume of revolution. Now we've rotated about the x-axis, so we must write that this is rotation around x-axis. Of course, there's no reason we couldn't rotate our function around the y-axis, and through a very similar argument we would end up with the following formula. Let's highlight that one in a different colour. So it's going to have the same basic form, and this one is the rotation around the y-axis. Now you would not expect a rotation of the same curve to give the same result. Clearly you'd get a very, very different shape if you rotated around the y-axis. Right, that's enough now. That's a little brief introduction to this topic of solids of revolution, and I would really encourage you to go and have a look at this GeoGebra website, and there are thousands of resources out there that much cleverer people than me have made, and you can find all sorts of topics, but this is a particularly good one with the three-dimensional modelling there. Thanks very much for watching. I'll see you next time.